last speaker is Christina Yu. Christina is an assistant professor at Cornell and a research fellow in the reinforcement learning program.
Thanks, Prasad. In this talk, we're going to look at the problem of episodic reinforcement learning with continuous state and action spaces, in which we have an agent interacting with an environment, and the dynamics and the reward function associated to the environment are unknown. So the agent is trying to learn the optimal policy as it interacts with the environment. But in this setting, we want to deal with the case of a continuous state and action space, where you have to figure out how to reduce the complexity of your space in order to learn. So one approach is to use parametric function approximators, but these suffer model mismatch loss and require prior knowledge of the structure in order to guarantee guarantee your convergence with respect to a particular model class. So instead, we're going to look at non-parametric assumptions on the value function with respect to some known metric. Next slide. One naive approach to deal with the continuous space is to simply uniformly discretize the space to map it to a tabular MDP. And oftentimes this discretization parameter epsilon is chosen as a function of the time horizon to balance the approximation error and the cost of solving the tabular MDP. This discretization can be very expensive though. Next slide. So we propose an adaptive discretization algorithm, which essentially starts with a coarse discretization of the space and only refines the partition as needed in a data-dependent way. So this generates kind of a sequence of tabular MDPs that locally refines the discretization only in areas of high value. So this reduces memory requirements and accelerates the learning. And I'll illustrate some properties of the algorithm just through simulations. Next slide. So in this problem, consider a simple oil discovery problem where there's an agent surveying a map in search of hidden oil deposits, and it collects reward according to the cost of transportation cost of traveling on this map, as well as a surveying reward related to how close you are to this kind of hidden oil. And to make it easy to visualize, we've chosen the unit interval to be the state and action space. On the bottom left, these two plots are illustrating the Q function, which is the expected value of the optimal policy for being in a state and action pair. And green denotes areas of high value and red denotes area of low value. And overlaid on top of these plots is the partition that our algorithm discovers. So the left is for the model-free version of our algorithm, the right is for the model-based version of our algorithm. And you can see that the partition our algorithm generates does in fact focus in on the regions of high value. And on the right side, on the right top plot, you can see that when you compare the reward, a collective reward from our algorithm as opposed to a naive uniform discretization algorithm, our algorithm in fact performs much better, converging faster to the optimal policy. And on the bottom right, it's showing that our algorithm in fact has a significant gains in memory savings. So it has a significantly smaller size of partition. And next slide. So in this plot, I'm just showing that we chose a different function for the reward function that's significantly more peaked, meaning that as you can see in the Q function, that there is a narrow region with high reward. So it's kind of looking for a needle in a haystack, but our algorithm is indeed able to kind of locate this narrow region of high reward, as opposed to the uniform epsilon net does not converge and in fact does not achieve the optimal policy, as you can see from the reward plot on the upper right. Okay, so that's it. There's one more example in the next slide, but I'll just show the slide and not talk about it. Welcome to ask me about it in the next breakout sessions.